lecture series for February. It's not often we get to talk about particle accelerators and particle physics, but it's an interesting topic that I know I enjoy reading about, even though I understand very little about it. So I'm glad we have an expert for it. So I would like to introduce the Department Chair of Physics at Oregon State University, who came to Oregon State, I believe, from Northwestern and formerly worked at Fermilab National Laboratory, Dr. Heidi Schellman, to talk to us about scientific collaborations at CERN and some of her ongoing experiments.
Okay, you guys can hear me? Okay, make certain this thing works. This thing has 3 buttons. It's actually 4 buttons. It's got left, forward, backwards, forwards, pointer, and damn it, which is when you hit the wrong button. Every speaker does this. Okay, so I was just going to give a little biographical detail. My parents moved to Oregon from Minnesota when I was 1 year old, so I'm not a native, but I grew up in Eugene, Oregon, and I then went away to California for 10 years to go to college, and then I moved to Illinois for 30 years. And 5 years ago, or 6 years ago, I was driving through there was a thing called the polar vortex. If you guys didn't have to deal with the polar vortex. It was like when it would get to be 20 below zero for a week, and then 2 feet of snow would fall, and I had a 45-mile commute, and at that point, Henry Jansen, who was the chair at Oregon State at that time, sent a message and saying, wow, I'm thinking about not being head of the department anymore. Anybody interested in my job? And I go, yes, I am interested in your job. So when I was in Illinois, I did my research at Fermilab, and my husband actually worked there as well. So I lived close to the lab, and I actually commuted to the university because I wanted to be at the lab more. And so that was cool because, I could just roll out of bed and get to the lab. So I moved to Oregon, and I didn't fly much back then. So I moved to Oregon, I moved to Corvallis, and suddenly I get asked to serve on the Scientific Policy Committee for CERN, which is I might add, it's a huge honor, it's absolutely fascinating, and it involves flying to Europe 5 times a year from Corvallis, which I'm sure you can appreciate how hard it is to get anywhere from places in Oregon that are not Portland, because you have to drive through Portland. Anyways, so that's sort of the genesis of this talk, is I'm going to talk to you not so much about my research, although I did some of this early on, but sort of what I've learned from my 5 years of going to CERN. So it's sort of a travel log. So first of all, what I do experimental high energy physics at both CERN and Fermilab. I do neutrino physics, which is reasonably low energy, and you aim these particles called neutrinos at a target, and you just see what interactions they happen. And I'm just realizing I didn't bring a neutrino up here. Maybe I have one in here, but I don't have a neutrino, so I can't show you right now. But I also do particle, proton, and antiproton collisions, and looking where you try to get the highest possible energy in a very small area of space, and then study what's comes out. And I'll try to explain why you want to do that, because it's kind of pricey, and I'd better be able to justify it. Okay, so this is a picture of my collaboration at Fermilab in 2005. And back here you can see the outer reaches of the D0 detector, and here's the collaboration, and I'm in there, so I'm there. And these are the flags of all of the countries that collaborated on the institution. This is not just the people who are in this. These are actually paying members. These are countries that were actually coughing up money to run this experiment. And I might add that a large fraction of this outer part was built by the Russians. So that's us. At that point, we had 550. I have 550 co-authors on my papers. And this group ended up publishing about 500 papers over a period of 20 years. So I study weak interactions, and the science I do are neutrino interaction experiments at Fermilab and proton collider studies of weak interactions. and in particular, a very precise measurement of the mass of one of the bosons, the W mass measurement. And I do some science policy, so I work on US neutrino policy, like where are we going to build our next experiment? What is it going to be? I'm supposed to be doing that. I'm not doing it anymore. Through the scientific policy committee, I've worked on things like figuring out how are they building these LHC, the Large Hadron Collider. And there's also something, this IUPAP Commission C11 it's an international organization that we're just sort of it's the physics, it's a union of a bunch of the national physics unions get together, and there's an international physics union, and I run the commission that is in charge of my field. It's a 3-year rotation. We all get to do it sooner or later. So that mainly deals with conferences and making certain that people get access to facilities rather than really setting major policy. So, but that's what I do when I'm not doing everything else. I also run a physics department, and if Aaron can tell you that's a time sink, right? It's a time sink. Okay, so what is CERN? Okay, it's an acronym in French for the European Organization for Nuclear Research. So back when they started in the 1950s, it was nuclear, it wasn't particle physics. And let's see, let's look at this. Okay, so this is Geneva, Switzerland. There's like the airport, and the River Rhone is sort of heading off this way, and CERN is here, and this ring here is actually 27 kilometers around. That is the full size. Basically, the CERN site is this little area here, which they pretty well filled, plus a little bit over here. And the rest of it is they actually just tunneled under Switzerland and France. And by the way, the French-Swiss border goes right through the middle of the site. And for example, the computer center is on the French side. And if you want to go there, you just walk across the border, because now that border is completely open. You used to have to go show your passport and maybe get your car searched. Now you just, nobody even knows where the border is anymore, which is kind of cool. So it is now the highest energy particle accelerator on Earth. It has more than 10,000 users and around 2,000 staff, and they have discovered 3 of the 4 heaviest particles we know about, the W and Z bosons in the 1980s, and then the Higgs boson in 2012. And I'm going to mainly talk about this one. It's also the home of the World Wide Web. The World Wide Web was invented at CERN to allow physicists to communicate with each other. And then it sort of seems to have caught on elsewhere. Okay, so if anybody asked me, like, what's this for? I go, you use this web thing? Okay, so why are we doing this? Okay, first of all, everybody knows about E equals mc squared, right? What it means is that energy and mass are equivalent. And what it means for us is that if you take a proton and whap it against another proton with enough energy, you can actually produce particles that are much more massive than a particle. So if you have a top quark, and here's a top quark, okay? And you want to make a top quarks weigh something like 180 times as much as a proton. So you'd have to get some protons that are very, very energetic. They have to be super relativistic. They have to have energies that are 180 times their mass, and you can whap them together. It actually doesn't work that well. So this is a proton, okay? Proton. Protons actually are composite particles. They have pieces in them. They have quarks in them. Like there's, what's this? That's an up quark. They got an up quark, another up quark. No, it's a down quark. Another up quark. So 2 up quarks, 1 down quark, and then some gluons to hold the whole thing together. So by the way, these are, there's an artist down in LA who makes these, and I've collaborated with her on creating some particles. I think actually this is one of the ones I collaborated with her on. It's called the Particle Zoo. So anyways, so what you do is basically the whole idea of particle physics is to get enough energy into a very small region of space so that you can actually make something new. Okay, so back to the control thing. So here it is. This is, not as quite as thrilling as this, but protons are not point particles. So if you have a proton, it's actually made up of like, 2 U quarks and a D quark, and then a whole bunch of, like, some more additional quarks and antiquark pairs, and then some gluons holding it all together, and they're basically just a mess. I spent 20 years of my life trying to figure out what the mixture of all these things in there was. An antiproton would be the same thing, except you just reverse the charge of each of these and make it the antiparticle instead of the particle. So antiprotons are very similar to protons, except all the quarks inside are antiquarks, where they would be quarks in the proton. So what actually happens at the LHC is they take proton number 1 here and proton number 2, and they collide maybe the quarks in here and the antiquarks in here, or a gluon from this guy with a gluon from that guy, and that collision of just what are called partons, these are just whatever little pieces are in here. When you actually have a collision between two protons, you're not really colliding the whole protons with each other, you're just colliding these little pieces. So of course, they're not going to give you the full energy, which means your protons have to be even more energetic. So, you know, at the LHC, often the things that are actually hitting each other, maybe 10% of the total energy in this guy and 10% in that guy. So you're really not getting the full energy, which is probably good, because it's a lot of energy. But that's how you get that's how you get enough energy in a small amount of space to make a collision, and then that collision can actually produce much heavier particles that then will decay and you can detect them. Okay, so that's what they're doing. So one question is, how do you get particles up to that energy? Well, you could sit around and wait for cosmic rays. There are actually particles that are accelerated in, say, supernovas and other places that are that energetic. In fact, the most energetic particles actually come from the sky. But in fact, what you really want to do is you build a very large accelerator complex. And so you accelerate your particles to near the speed of light. You trap them in a circular ring with magnets. And so here they are. They're going to trap your protons in this ring here, and they're going to go around in circles. The magnets will steer them around in circles, and then you have an accelerating piece maybe here that every time they go around, it gives them a little kick. And sooner or later, after a few seconds of going around this again and again, as long as you trap them and you ramp the magnets up, you can actually accelerate particles to very high energies. Problem is, as all the people taking, I guess it's physics 213 here? Is it 203 or 212? No, I mean just electromagnetism. Yeah, so if you're taking 203 or 213, you know that the more energy or momentum a particle has, the harder it is to bend. So what you end up having to do, if you want higher energy particles, you have to get stronger magnets, and the LHC has magnets that are a factor, I think, 4 stronger than the ones that were originally built at Fermilab, and you have to make your ring bigger because the things just don't want to bend. So that's why it's so big. So you need to have these very large rings of very expensive superconducting magnets. These magnets they put in there are much stronger than the ones in MRI machines, for example. And they just they had to develop the technology just to make this thing work. So you have stronger magnets and bigger rings, and of course that starts getting a little pricey. So you end up, over the years, what's happened, people started out with experiments with like 4 people on them. These experiments now have 3,000 people on them because you have to pool the resources of entire nations in order to get enough money to build something this fancy. I might also add that it starts out with a little bottle of hydrogen here. And they ionize the hydrogen and they put it through one accelerator, and then it goes over here to another accelerator, and then it goes over here to another accelerator, and they finally shoot it into the big LHC. All of those components have to be working in order to get this thing to work. They're going to add something called LINAC 4 to this, which will eliminate a couple steps, but it's a very large and complex system to get this going. But it works. About 50% of the time, it actually does everything you want. Okay, and then once you have managed to make these proton beams and accelerate them to very, 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 very high energies, you then have to take those 2 proton beams and you have to aim them at each other, squeeze them down to 1/5 the size of a human hair, and have them hit each other. That is not easy. So here it is, they have these beams and they focus them down and they also steer them so that they actually hit each other. And you basically do not want them to not hit each other. These things all have to hit each other. This interaction point has to be at the right place to within maybe a millimeter over 5 kilometers. And one of the things that happens is that this is a pretty delicate process. And for example, an earthquake can perturb the ring enough that the beams can actually just fall out of their orbits or just stop hitting each other, but even possibly fall out of their orbits. And so one of the things that used to happen at Fermilab is when there was an earthquake in, say, Alaska or Baja California, they'd actually turn off the machine so that you wouldn't have to worry about the seismic effects messing with the beam lines too much. The CERN accelerators are known for being sensitive to things like the train going by and storms in the North Sea and the phases of the moon, because all of those will take that big ring and they will stretch it and compress it enough to perturb this kind of alignment. Okay, so that's just a picture from a 2010 earthquake in Baja California that showed up in Illinois. And you can see there was an earthquake. And I don't even want to talk about the one in Japan. I also have that trace, but that one basically was really serious. Okay, so the energy here is, well, I should, someplace I have something where I explain the energy. Maybe I've already skipped it. So basically what you do is you want to get as many collisions as possible. So what you do is every 25 nanoseconds, you inject a bunch of protons in, and every 25 nanoseconds, you have a bunch of protons going one way, hitting one, going the other way, and 25 nanoseconds later, another train goes. So there's something like 2,000 of these bunches of protons going around that ring, and they're spaced 25 nanoseconds apart. So that's a bunch crossing. And then when those bunches cross, you can get up to 40 protons in the bunches of protons colliding with themselves. And normally when the protons collide, then you get some of these partons colliding with each other, normally maybe 1 or 2 there. And then we hope that we're going to get some new particle coming out of it. So you start out with bunch crossings that are happening once every 25 nanoseconds, which is 40 million times a second. And in the end, you get down to something like once every day, you get something interesting like the production of a Higgs boson that you can detect. So another thing is you want to get as many collisions as possible. These things are really hard to turn on and off. So once you've turned it on, you generally tend to run it 24/7 for periods of 6 to 8 months. After that time, enough stuff is broke, you can't keep going, so you have to stop and go in and twiddle with things, but that's how it works. When you turn one of these things on, it takes a month to cool it down to cryogenic temperatures, and then you just run that thing and you try not to touch it. Okay, so I'm going to give you some history of CERN. Is that there was this thing called World War II, and this is kind of what it looked like at the end of World War II. A bunch of Europeans decided they needed essentially a team building effort. And so there was a decision to try to build an inter-European research center that everybody would contribute to and everybody could go to. And it's a very idealistic plan in the context of Europe after World War II. It actually predates the European Union in some sense. And it still is an international laboratory that is essentially open and supported by all of Europe. And it's actually a very strongly held belief in Europe that it's a good thing, which is good because that's what keeps it going. So they decided to build this, and let's see. Oh, I'm doing the light thing. Okay, so they have, of course, it's an international organization, so they have 3 years of diplomatic discussions, and where are you going to put it? You're going to put it in Denmark or Paris or someplace in the Netherlands or Geneva. In the end, Geneva won out, and it was 12 European countries with Yugoslavia at that point. And then the question was, how are you going to pay for it? In fact, the countries decided to stump up the bucks to do it. And here's the groundbreaking going on. That actually looks more like some farmers, doing some farmer things there. That just looks like a tractor to me. So this is what it looked like in 1959. And we're going to see this building here again. But this is the first accelerator they built, and they're just starting it out there. And these structures are still there. And these buildings here, that's building 1, that's building 2. They're pretty ratty. When you see films about CERN, a lot of them is filmed in those because they're kind of grotty-looking, picturesque science buildings. This obviously used to be normal farmland. It's now vineyards that actually produce a pretty good white wine. This is the central building under construction. The bit of a problem, which I'm sure this place will run into, is this building is actually kind of falling down. It was built in like the 1959 to 1960. It's kind of modernist, but it wasn't, the construction quality is not that great. It's great to be in, but it's kind of crumbling, and it's now considered to be so iconic as a symbol of international scientific collaboration that they can't knock it down and put something decent up. So that's a bit of a headache. You don't want your building to become famous. Okay, this is actually a picture, a recent picture. It's actually in the opposite direction. It's looking the opposite way. So you're actually looking this way now of the CERN site. So here is that building. Let's see, where's that building? It's in here someplace. Yeah, there's that building, that same building there, and the dormitories are here. They've added dormitories. That ring you could see barely there is now here. The Atlas experiment is over here, and they now have this dome, which is a real landmark in the area. And the French border is kind of like here-ish. And here's a bigger one, a zoom out. There's that same site. We were looking that way. You can see that original big circle there. And then you can see all the rest of this stuff. And so there's France, and there's Switzerland, and CMS experiment. Atlas is right across the street, so you can just walk to the cafeteria and hang with your friends. CMS is over here, and if a French farmer on a tractor decides to not be your friend, you can take a very long time getting to that laboratory. Okay, so down in the tunnel, which is underneath this, it's about 300 feet below the surface. This is what it looks like. These are the very large superconducting magnets that were built worldwide. Some of them were built in the United States. A lot of them were built, most of them were built in Europe, and there's all the services that go with it, pipes for liquid helium and electronics, radiation detectors, and this is actually a special railway they have for the little fire trucks that they can take around to go around the edge. And a sign of the international organization of this place is that these guys are called the pompiers. The pompier is a French, for pumpers, the French word for firefighter, and they've always been called the pompiers, except now they have signs that say, you know, fire and rescue, and they speak English, which was a shock to me. I was in the cafeteria, and there's a bunch of dudes speaking English, and it's these guys, and they're Englishmen. So part of internationalization. So when they decided to build this LHC thing, once again, it's 300 feet below the surface. So what they did was they built, this is the main shaft for lowering the detector down into the tunnel. So the tunnel is 300 feet below that. There's a little access shaft for things like elevators and escape routes and stuff like that. But, you know, this is a very large crane, and digging these holes was hard because it turns out there was an underground river that they discovered when they did it. So that sort of messed up the schedule for a while. But that's one of the things you do in the particle physics thing is you build these very large shafts. So here's looking down one of those shafts. Yeah, so there's like ventilation or something here, and there's some lowering rigs, and then down at the bottom is a hall that is much bigger than that. The hall is maybe twice the size of this room at the bottom of it. So here's the same view looking upwards through that shaft and at some of the scaffolding when they were building the hall below. And this is what we're looking at here is probably 2003, 2004 type time scale. And then here is a detector that you may not realize it, but it's almost as big as that shaft you saw. This is the CMS detector, and this thing is probably 30 feet across, and it's basically made out of steel and uranium and lead. No uranium, lead and steel, so it's really heavy, like several thousand tons. So you lower this several thousand ton object 300 feet underground, and then this is one of the end caps. So this gives you some idea of the scale of this. This thing here fits into there. So, and these are two people next to it. So that gives you some idea what this thing looks like. These things are huge. The experiment I worked on was probably half the size of this one, and that was huge enough for me. Yeah, it's really fun climbing on these things back when we didn't have decent safety equipment. So here's another picture of that same detector with, so these are the, once again, like these are the things that were lowered down through the, through that shaft, and then this is one of the end piece that then slides into here. When they're working on it, they pull the end pieces off. There's the beam pipe that the beam circulates in, and there's a person. All of these things here are detector systems, which are detecting particles that are coming out of the central reaction. These things were, they approved construction, I think, in 97. At least the US joined the project in 97, and it took them till 2011 to get this thing all working. So here's a picture of some people sliding in the most central part, which is a very, very precise tracking system. And then out here is more tracking systems. There's a very large superconducting magnet here, and then a bunch of detectors that just detect energy deposited. After you've tracked particles as far as you can, you then just, you know, let them blat into something and measure the rest of the energy. But this is one of the, this installation step where you're putting this part in is where you really don't want to mess up. This is actually the other detector, which is even bigger. So there's a person. These are very large superconducting magnets that are used to analyze particles that make it all the way out of the detector. And you can see over here the stairs. This thing is something like 10 stories tall. And when these magnets are on, you are not anywhere near them. Okay, so this is the CMS detector. That's the one I've shown you most of the pictures of. The action is actually happening right here at the center. Beams come in this way, and they come in this way. An interaction occurs in here. A bunch of particles come out. Several hundred particles are produced. They come out. And this inner volume here is magnetized, and you can actually see the tracks of charged particles, and they bend in the magnetic field. And because they bend in the magnetic field, you can actually measure their momentum, and you can estimate how much energy is coming out. And then the rest of it that's surrounding it is what's called a calorimeter, where once a particle hits that, it just deposits all its energy in the calorimeter. And so you can get a pretty good estimate of the total energy that was produced in the interaction and sum it all up to see what was the total energy, but you can also see what direction individual components were coming. And it's quite precise. So lots of pieces. The US built some of these pieces. I mean, the US actually paid for and constructed about 1/4 of this total detector, including actually this guy here. This is a pixel detector. This is actually being replaced right now with the new version. But what it is basically 65 megapixel camera is one way of putting it. It's got little silicon pixels. Each of these guys is covered with silicon chips, which have pixels on them. It's sort of like it's like the ones in the back of your digital camera, except there's 65 million of them, and it can read out at 40 million frames per second in bursts. You can't store 40 million frames per second, but what they do is they store about 10 milliseconds worth of, microseconds worth of data, and then they have to figure out, am I going to keep it or I'm going to throw it away? But in fact, it is one hell of a fast camera. And that was, the original mechanical design was actually done by the Northwestern group when I was working there. I didn't work on it, but there were pieces of this thing lying all over the lab for years. And it also, there's a central region that looks like this. These detectors were invented in the late 1980s and have turned out to be the workhorses for the field. And they allow you to measure what's going on in the interaction on the scale of microns, human hair type measurements of what's going on in interaction that then proceeds to go, many meters. So these are very cool and, hard to build, and they produce a huge amount of data. So this actually shows you, this is a control room when something exciting is happening. These things have to be staffed 24/7, and normally there'd be 3 or 4 people in there, nothing exciting. They're obviously turning something on or off when this happened, although it can't be the most exciting, because otherwise it'd be completely packed. So this is the Accelerator, and then the ATLAS and CMS experiments have their own little things here. And all accelerators have these things with, 50 monitors showing you all sorts of fun, cool stuff. Okay, so let's get some physics, and let me see how much time I have. Okay, doing about okay. Okay, so here's our standard model of elementary particles, and I'm going to go through and explain what the various things are. Okay, so first of all, matter. Matter is made up, so the matter is made up of the stable particles, the U, the D, and the electron. This is what protons and people are made out of. And then you actually have heavier versions of the U and D quark, like the C and S quark and the T and B quark. The S quark is the strange quark, and I actually have this guy here. People who near the front can see that it has 3 eyes instead of 2 because it's strange. Yeah. It's heavier. Ooh, this guy's actually lost an eyeball. Oh my God. I'm gonna have to send him back. Okay, so this guy should have 2 eyeballs. This one has 3. So that's one of the heavier ones. And these guys are short-lived, and they actually decay to these guys pretty quickly. And there's also the electron has has 2 heavier analogs, the muon particle, which lasts about 2 microseconds, and the tau, which actually lasts femtoseconds. And we've actually, though you use those silicon detectors I was showing you earlier to do things like measure the lifetime of the tau particle. Okay, so that's the matter particle. So as far as we know, all the matter in the universe is made up of those kind of particles, normal matter. Okay, so there's things called force carriers. Electromagnetism is just, from our point of view, it's just photons. There's also the strong interaction, which is carried by gluons, and then there's the weak interaction, which is actually carried by these very massive particles, the Z and W, which were discovered at CERN in the mid-'80s. And I'll go into a little more detail on what these guys are. And then finally, there's our little friend, the Higgs boson down here, which is essentially what seems to give the rest of these guys masses. And that thing was hypothesized in the late 60s, early 70s, and people waited, and people spent years and billions of dollars trying to discover it, and it was finally discovered in 2012, and everybody was very happy. Okay, so a little bit on how forces work. So the basic idea is all of nature, our model is that all of nature is made up of these fundamental particles, and in fact they interact with each other in very simple, well-described ways. They're called the Feynman rules for the model. So for example, if I have a neutrino particle here and I want it to interact with a D quark, well, it could do this. It could scatter, it could emit a Z0 boson here, and that Z0 boson would scatter off the D quark, and so you're transferring some energy and momentum between this guy and that guy by the Z boson, and so the D would get deflected and the neutrino would get deflected equally. So that's our model of how all interactions work. Same thing here, actually it gets a little more interesting because it could come in and it could emit a W boson, which has a charge. And then you have to preserve charge. So you have to have the neutrino has to change into a mu minus particle, which is allowed if it's through a W. And then the D quark has to change into a U quark, and that preserves charge. But this is how forces work. And all of particle physics is basically figuring out what those interactions are and kind of, sticking them together like Tinker Toys to make whatever interaction you're interested in, and then you have to calculate what the probability of it happening is. But that's why somebody asked me early on is, do we do much quantum mechanics? It was not really. I mean, you actually end up treating these quantum mechanically, but underneath it all we really do is bounce things off of things. Okay, so you can combine force carriers and matter particles to make complicated interactions. So you have rules on what interacts with what, and generally the more complicated an interaction is, the less likely, because you have to have more of these bits and pieces together to make it work. But as long as you actually observe all the conservation laws, like charge has to, if you got charge coming into an interaction, the same amount of charge has to come out. If you have energy coming in, same energy has to come out. And various other particle numbers like quarks. If you have a quark come in, you sort of have to have a quark going out. basically, once you've obeyed the basic rules, you can write more and more complicated interactions, and they become much and much less likely, but they're still possible. So we want to make a Higgs boson, and the problem is this. For making a Higgs boson, I'm going to explain this. This is how you make a Higgs. You take two gluons, which are massless, strongly interacting particles, and they collide to make a top and a top triangle here, which is perfectly lit, which is it, you know. There's tops, the charge is conserved, top number is conserved, gluon number is conserved, and then the tops annihilate to make a Higgs. And then the Higgs decays into two Z bosons, which then decay into some lightweight particles. This is actually how you find Higgs boson. It looks really Baroque. It is, and that's why the probability of this happening is something like 1 in 10 to the 14 per interaction, because you do have to go through all these complicated steps. And the reason you have to do that is Higgs bosons like mass. They could care less about a massless gluon. You know, they are not going to hang with massless gluons. Not happening. They like top quarks and Z bosons. But gluons actually are strongly interacting particles. They like quarks. And they don't care if it's a top quark or a U quark or whatever. They're going to interact with top quarks. So the moment you can get a gluon to make a top quark, then you can make a Higgs. And then once you have the Higgs, it's going to only decay to things like Z's and W's. But then those Z's can use the normal weak interactions to decay to lighter particles. So to get from light particles to heavy particles and then back down again, you have to go through this long stream of consciousness. Okay, so that's how you make a Higgs. And the probability of making a Higgs is way down here. This is rate, and it's a log scale. And this is like 10 to the minus 3, and that is 10 to the 10 or something up there. So the odds of making these is pretty low. But in fact, it's possible. And this is how you make a Higgs that decays to two Z's. And this is how you make a Higgs that decays to two photons. So those are two different signatures. One is 2 photons, and the other one is 4 electrons or muons. This is what it actually looks like in the kind of, when they did the discovery, is here's 2 protons are going they're going this way into the board or the screen. And the reason you see these things bending is because there's a very strong magnetic field that's also going into the board. So any charged particle that's going perpendicular to that magnetic field is going to curve. And that's how you estimate the energies of these particles, is by how much they bend here. And in this case, the Higgs has decayed into 2 electrons and 2 muons. And those actually reconstruct to have the masses that are kind of Z-ish, not exactly. But there's a Higgs has happened in the center, and it's decaying to these 4 leptons, and you can add up the energy and momentum of these 4 leptons, and you will find out it has the energy and momentum of a Higgs boson. Okay, let's see this. This is another one. This is from a different experiment. This is actually a Higgs that's just going into the 2 photons. Here's 2 photons coming out. You can tell they're photons because there's no track. A photon is a neutral particle which just has energy. It's the same thing it's what's coming out of the light bulbs here. Good thing they aren't charged, otherwise light bulbs wouldn't work. So in this case, you have 2 particles that are chargeless, so you don't see them in the tracking system, and then a huge amount of energy shows up on the outside. Okay, so this is actually what happened when they were taking data. The black points are the data. The red points are what you'd expect if there were no Higgs. So this is what you would expect if there were no Higgs, is this red stuff and a little bit of this purple stuff. And then you'll notice something going on here, and it's actually showing up as an excess here. This at 125 GeV, which is 125 times the mass of a proton, basically, is the Higgs signal. So that is in the ZZ, the 4 lepton channel, and that's this process here. So, by the way, this is like, a year and a half of running. Nowadays they can do this in a couple months, but this is a year and a half of running after you spent 15 years building the experiment, and everybody just goes hysterical because they finally found this thing they've been looking for 15 years. So let's do that one again, and then I'm going to show you another one. Okay, so I think there's another one. This is the photon-photon, which is much harder. Although the signal is actually larger, the backgrounds are much bigger. So let's wait a little while here. It takes a while. There it's coming. Yeah, people got pretty excited at the wrong mass earlier on. So if you look at it, there's a little bump. There it is. And that's a lot's gone on. They haven't updated these plots to include the new data, the much larger data samples. So, okay. Maybe I don't get to give. Okay. So there is Fabiola Giannotti announcing the Higgs boson. She was the spokesperson of one of the experiments. She's now the director of CERN. And she is like the politest person I have ever met. She plays classical piano wonderfully, and I once shared a dorm room at a conference with her, and she brought her own coffee from Italy for us. Just a fantastic roommate. And brilliant scientist as well, but also very nice. So this is, once again, I was talking about, I showed you the D0 experiment. There's actually a reasonably large overlap between those groups of people. All the D0 people, except me, ended up joining one of these two experiments. So there's a lot of familiar faces in here. They're actually up on the surface posing in front of a picture of what the detector looks like. This is a full-scale picture of the detector, but the real one is 300 feet below them. So at this point, I'm sort of going to go on a sort of tour of what it's actually like there, just to give you some idea. So this is the computing center. Processing the data from these experiments takes somewhere between 100 and 500,000 cores. They now have something like Atlas at home where you can actually do some of their work for them. But it's a very, very large-scale computing effort, and they've built an amazing international infrastructure for sharing computation, which is now shared with other fields of mainly physics, but some biology. So scientists can actually take advantage of the infrastructure that these people have developed. And I do a lot of work with these people. I'm now an observer on the board that sort of oversees how they do this computing. But this is kind of, this is one of them. They actually have other sites. These are like air cooling and heating and stuff like that to keep everything going. And a lot of this is disk drives, but it's also just rack after rack after rack after rack of computing. And there's probably maybe 100,000 cores in this room. And then they use facilities worldwide. They also have tape robots that are quite large. So yeah, so this is an example of the Atlas computing activity from 2017. And this is what the international community promised, and this is actually what they got. So one of the things is people tend to other people don't know how to use the computing system, so we generally get more of it than you would think. Most of that is simulation, just trying to simulate what you expect so that you can compare it with what you're seeing and compare different models. This is actually the SPC. This is kind of the management board for the whole laboratory. There's Fabiola and, well, I'm over there someplace, but there's all these people. There's, all the heads of divisions and representatives of most of the European countries and a few experts from the United States. And representatives from some of the other countries are there. So this is at the top of that weird-looking building I showed you early on. Somebody once walked out of this with this thing. That wasn't popular. Okay, so now I'm going to go into what it's like there. So it's just sort of a photo montage. Okay, so first of all, one of the cool things about CERN is that it is near Mont Blanc. And if you are sitting in the right table at breakfast, this is me sitting inside at breakfast looking out, and that is Mont Blanc. That is a 16,000-foot peak. And I have other photos with like sunsets glistening off the glaciers of Mont Blanc. But you can basically see one of the most spectacular, I think it's the largest mountain in Europe. You can see that while you're eating breakfast in the cafeteria. And they have this nice outdoor region, which I am not using right now, but in the summer it's quite nice. This is what the cafeteria looks like at lunchtime, and it's actually a bit of an understatement. Something like 1,000 physicists crowd into this cafeteria at lunchtime, and they don't believe in soundproofing in Europe. All of the surfaces are hard, wooden chairs, wooden tables, no carpet, not much soundproofing, and there is deafeningly loud. All these people, and the people run into each other, it's pretty wild. And that's one of 3 seating areas. The salad bar is really, really good. So there's some sardines, there's some lentil salad, there's a pate, a little salmon, and it's subsidized, so it's pretty cheap too. And this is where the difference between American and European science comes in. CERN has 2 pastry chefs. Nobody in the United States has 1 pastry chef. They have 2. I will say, some of the other food isn't that great, but oh my God, the desserts. Okay. The sandwiches actually turn out not to be bad. There's a nice little avocado salad there. This is a duck and brie sandwich for about $6. Oh yeah, and note the nice little, toothpick, fancy toothpick and an apple. The French and Swiss know how to live. Okay, so they have 4, and now they have 3 more out in the hallway, automatic coffee machines. And there is always a line for those 4. You do not just walk in there and get a cup of coffee. There is a line for those machines. And this is a disaster. This is one of the coffee machines, and they've shut it down, or it's having trouble, and you have to know the password to get it to work again. I have seen physicists cry when confronted with the only machine left has the password, and they don't know the password. Okay, this is a really nice summer day. It's not super hot. You can see people are wearing jackets and stuff like that. One of the problems for CERN, which is also something that's very common here, is the climate is actually very similar to the Willamette Valley. They didn't believe in air conditioning either. So, most of the offices have no air conditioning, and it can get pretty steamy at this place. So it's one of the reasons people sit outside is, this day it wasn't that hot, but a lot of hanging out outside happens there, partially because it just becomes stifling inside. They have a orange juice machine that will take 4 oranges and squeeze them. It's like 3 francs or something. So $3 will get you a nice glass of fresh squeezed orange juice, and you can actually see the robot make it. This is a view from that top building towards the mountains, and reasonably late at night. It's probably 4 or 5 p.m. People tend to come to work later and leave later in Europe. They eat dinner later. So there's, as you can see, there's quite a lot of people left there, and this is probably 5:30 at night. And people working away. Once again, spectacular mountains. This is actually looking away from Mont Blanc. I will point out that not all buildings and roads are shiny and new. These are basically porta things that are reasonably good. These are really ratty. The pavement looks a little beat up, etc. It's actually not all glamour there. There's another view of Mont Blanc. This is coming back from the computing center. You can see the mountains there. And that's actually got the sunset on some other peaks. This is a sign that says in French, "Do not come into my lab and try to clean up." A little bit sexist. You're not allowed to do that anymore, but it says, "Don't mess with me." This is a prototype detector. They have all these amazing prototypes that they build. This is a prototype that some of my colleagues have built, and what it has underneath this is a vat of liquid-argon at, 77 degrees Kelvin that they're using to read out particle tracks. And they're trying a new technology here, so this is a bunch of instrumentation to tell what the temperature is, and there's all sorts of liquid helium and liquid nitrogen and all sorts of stuff going in there. That was the first phase. That was the small version. It's about the size of a car. And then the new version is this thing, which is a little distorted in this picture, but it's basically about 3 stories tall. And yeah, here's some people to give you scale on that. So this is a similar detector, except it's now been scaled up. So this contains about 700 tons of liquid-argon. And it's running right now. They're taking data, and this week. And this isn't a building that's about the size of a football field, and there's actually particle beams that come in this way and can be steered into this detector. This one didn't get working in time for the particle beam, so it's going to get fired up again with beam in about a year. This is what the interior of one of those things looks like. Once again, this thing is it has 700 tons of liquid argon at cryogenic temperatures, which means you have to have one boatload of insulation. So another thing is that so what's in here is this is actually you also have to, you can't just put it in styrofoam. You have to have something pretty solid to contain it because you don't want the stuff getting out. So what you do is you actually have about 2 feet of styrofoam and plywood on the outside here, and then you coat it with this metal. It's an aluminum coating. It's about 16th inch aluminum, and the reason it has all these bends in it is because when you freeze it down, it's going to change shape. It's going to compress, and so you have to have enough give in it so that it can compress. This is the technology they use to move liquid nitrogen, liquid natural gas. Those big tanker ships use this same technology. So we just adapted that technology for this. They're much bigger, but you actually have to worry about things like, when you cool something down that much, it's going to get a lot smaller. So a lot of insulation. You can almost see it here through the door. And then in the end, you just weld this thing shut, and there's a few things where you can put instrumentation in. This is just a picture of what the hotel looks like. It's 58 Swiss francs a night. By the way, 58 Swiss francs is basically 58 bucks. Nobody can sleep in Geneva, Switzerland for 58 bucks a night. It's normally 250 bucks. It's one of the most expensive cities on the planet. There is no TV, there is no AC, there is steam heat and a shower, but it's pretty nice, actually. These are just like, for example, when you have these kind of cryogenic systems, you have to keep them cool. You need a lot of backup generators. So this is a very large bank of backup generators. Let's see, get a little further. This is actually they do some medical physics. They produce isotopes, and they also do some medical physics studies here. And this is the slide. This is one of the tourist attractions. This is where the public can come and visit this. And yeah, they got a herd of sheep because, why not? So that's it. So thank you very much, and I'm ready for questions. And apparently there are people in the great outdoors watching, and so this is being streamed, so we're going to need people to wait for the microphone if they have a question. So who has the mic? Okay, so we had a question over there. Oh, I forgot. Here's the Higgs. This is actually older than the real Higgs particle. We used to hide it in the detector just to mess with people.
Does anybody use cloud chambers anymore?
Well, let's see. Do people use cloud chambers? We use similar things. I mean, basically a cloud chamber works. People use what's called bubble chambers. We still use those. So cloud chambers were something where you got a supercooled gas, like a vapor, water vapor, and when a charged particle went through, it would actually cause the supercooled gas to nucleate into liquid drops, and you could take a photograph and you could see it. So people do have cloud chambers for demonstration purposes, but you can do the exact same thing with a liquid. You take a liquid and you superheat it, so that when a charged particle comes through, you'll form bubbles. And there's actually people doing dark matter searches in Sudbury where they use that technique, and they also listen for the bubbles. So they use photographic techniques. They basically have a vat of a liquid, and when a particle is produced, it would produce bubbles, and they can both photograph the bubbles, but they also can listen for the bubbles. So yes, people use a similar technology. I don't think that anybody actually uses cloud chambers themselves. We use similar ones, but not exactly that.
So I know CERN is, CERN is turned off for now. So what's the future? I mean, what are they? They're upgrading it from what I understand. So what are they going to be doing next now that they found the particle? It's like, okay, what's the next exciting thing to do?
Well, the problem we all I'll have is that, we now know that the matter particles are only about 5% of the universe, and that there's, for example, dark matter. We don't know what dark matter is, and it's kind of annoying that you have this perfect model that can describe everything we see in our experiments, but you know that it's only doing a very small fraction of what's actually out there. So what they're looking for in the future is to try to find new particles that we just haven't been able to see yet. And that's what you do. 30 years ago, they used a similar machine to find the W and Z boson. We used a similar thing to find the top particle. You just have to get enough energy in one place and log enough interactions. If there's something there, you're going to be able to see it. And they've actually managed, unfortunately, they've managed to rule a lot of the candidate particles out so far. But that's what they're doing. They're in exploration mode at this point. They can also do some very nice precision measurements, like the mass of the W better than I did, although I'm waiting. There are precision measurements they can do of just standard science, but that's the main thing, is they're really going for the things they don't expect. We didn't know what the mass of the Higgs was. We were almost certain it existed. So that was kind of it's like discovering the North Pole. You know it's there. It's just really hard to get to. But if they discover one of these new particles, we just know that stuff is out there. We just don't know what it is or how to find it. So that's what they're going for. They're going for higher energy and factors of 10 to 100 more particle interactions. And that's taking a lot of upgrades of the detectors. The next run is just going to be more of the same. They might try to bump the energy up a little. And then in 2026, they're going to turn on with upgraded detectors and a much, much more powerful machine. And that's where they start looking for the new stuff.
Can you talk to me a little bit about the computer storage? You said that they can only take so many images because of storage.
Yeah,
would they be able to discover more if they could store more? Or?
Yeah. I mean, that's always a battle between us computing people and the experimentalists, because they want to write more data, and we're sort of like, we can't put it anywhere. I mean, they. So it's always, people keep on trying to get more and more clever. A lot of what they're doing now is what happens is you take the data and you what's called pipeline it. You basically store like 10,000 interactions in a pipeline, and then you try to run algorithms that allow you to tell if there's something interesting going on. And then you go to the next level, and the next level you then have to make more decisions, and in the end you have to decide whether you're going to write it to tape or not. And yes, all of those decisions involve making some kind of judgment about what you're doing. So what you will often do is, like, every time you make a decision, maybe 1% of the time you won't make the decision, you'll just write the answer out. And so you do have some unbiased samples, but an unbiased sample of 1 in 10 to the 12 is not very useful. So yes, there are biases in what we do, so people tend to try to look for things that are as unbiased as possible. Basically, in this case, you look for large energy and weird combinations of things you normally wouldn't expect. Like if you see 3 electrons and 2 muons, that's probably an interesting interaction. So you'll often be looking for the rarer particles, because that'll be a sign that it's more interesting. You'll keep those guys longer. But yes, you really are, they actually end up writing, at this point, when I was starting out, you could write out about 20 hertz, means 20 times a second. The ATLAS experiment now writes out about 5,000 times a second. So, we've gotten a lot better, but 5,000 times a second is not a trillion times a second or 1 billion times a second, which is what they should be doing.
Does anybody else have any questions?
Okay, good. They're all going to come. Oh,
I will take this time for a second to thank you again, Dr. Schellman, for coming in and giving this talk. And I'd actually like to ask all of you, as you get ready to head out to the rest of your evening, feel free to make sure you sign in out front. And also there is a there is a small donation box if you want to donate to help continue this type of lecture series. We're always looking for assistance in that regard. So if you feel like donating, be my guest. I actually want to give our department collaborator, Crystal Hopper, a little bit of a chance to tell you about some of the stuff that our students here at SWOCC are doing in the physics and engineering departments that you might also be interested in before you head out on your way.
I actually wrote notes this time because I've had a long week. It's only Wednesday. I just wanted to thank you for coming. This is exciting for us to have, having an astronomy and physics lecture series. We had a couple people that came in today that didn't even, like, oh, wow, did you guys just start this? We've had a few of them, but, and we love Ron's geology series. Actually, our first one was with him. And so this has just been exciting, and we've got several awesome speakers lined up. So please follow us on Facebook if you're on social media, or we try to get it out in the newspaper and news, or we'll try to post things around the campus. Just help spread the word. We've got a lot of exciting things happening over here at in the physics department. We have our SCORE students, or we have one this year that through the help of the Oregon Space Grant Consortium, he's doing some solar physics research. We also have our SPEAR team, who is working with mini satellites. We just got some parts in, and we just had a meeting yesterday. Before, if you've seen, we actually had the high altitude balloon launch. Our last launch was amazing, got up to like 90,000 feet. And it was our last one so far. And so that was really exciting. Dr. Coiner has been doing some community outreach, not just with this, but also for the kids over at the Boys and Girls Club. Has STEM explorations currently going on once a week right now through this month. If you're excited for kids to come learn, just pass the word on for that. Also, he does some talks over at the Coos Bay Public Library. We have just, if you have some ideas of things and ways, if you want to have Dr. Coiner come speak, and just get a hold of us and let us know. The experience with SPEAR and with the SCORE. I didn't even mention Invent Oregon. Our team last year went all the way to the finals. They did amazing. Invent Oregon is chance for, along with SPEAR and the others, them to get hands-on experience, and it looks great on college applications, scholarships. So just a lot of exciting things happening. So just wanted to say thank you for coming again, and just follow us, like I said, on Facebook if you're there, or just kind of help spread the word and all the things that's going on just here in Coos County. Thanks.